exponential functions. These are well, a lot of times, but you got to make sure that you understand the formula. Okay. The one thing that most students, I should say, don't keep in mind, and because they don't use them quite a bit, that's fine, are the laws of exponents. You got to remember that exponents are kind of like how multiplication works. You know, multiplication is repeated addition, correct? Exponents is repeated multiplication. So from that perspective, I mean, you take a look at things like what I have here. A to the s times a to the t, they just get multiplied together. Or get added together, I'm sorry. I was looking at the next one already where they get multiplied together. Okay. So that just means that I have this many of those. Distributive. 1 to any power is just simply 1. This is usually the one that kind of throws people. And I do like the idea of writing it like this because it kind of helps students see that it does go both ways. If you have something in the nature of, a to the negative 1, that means that it's going to be the same as 1 over a. If I want to put it to the negative n, that just means it's just going to be a. Yeah. Can I put any fraction that I like over, or any number that I like over 1 and turn it into a fraction? So I like thinking about it like this. We're dealing with these in terms of rational expressions. Think of a numerator, think of a denominator. If I have a negative, it allows it to go down to the bottom, the positive. Likewise, if I would have 1 over a to the negative n, what would that look like? That would look like a to the n. Could I put it over 1 again? So the negative allows us to move things from the numerator to the denominator. Essentially what it allows us to do. Okay? And of course, anything to the 0 power is 1. Now, mind you, I do state that, a little bit of a qualification there, but if you generally think of getting something to the 0 power, 1. You guys know why? Let's say I have, we got a to the n, right? Is that equal to 1? Same thing on top, same thing on the bottom. If I go and rewrite this idea with what I have here, if I decide to go and take and move this up here, that means I would end up having a to the n multiplied by a to the negative n, correct? And according to our rules, if I have things multiplied together, I add the exponents. So if I add the exponents here, I end up with a to the 0. This is why anything to the 0 power goes to 1. Okie dokie. Okay. So, exponential growth. That's a good thing, right? So if the value is going to double with every increase for every 1 unit. So if I just look at the table of information, you get 5, 10, 20, 40, 80. You keep multiplying it by 2. That's all that we're telling you to do. So that gets us down here But what did I start with? I started with 5. So, and if x is 0, anything to the 0 power is 1, 1 times 5 is 5. This usually leads students to a problem of learning how to count. When we are dealing with this, the first thing turns out to be x is 0. Their starting point. After you do the first thing, then you get something. So 0 turns out to be the starting point for us. So, something to keep in mind. Exponential form is going to be like this. CA to the x. C is a real number. A is the growth factor. C is our starting point, and if we make sure that we use x starting off with 0, we're fine. So, let's see. These are the fun ones. That makes sense? My question for you is, what is x and what is x plus 1? What do those do? What is x supposed to be doing for us? What does x mean? When we are looking at things in terms of a function, what does the x represent to us? Okay. We got to change. But what is generally x identified as? It's a variable, you got that right. We're changing it. But what variable? Input. Okay. So it's basically how we are counting things from the first, the second, the third, the fourth, the fifth, the sixth, right? So if I have x plus 1 on top and x on the bottom, what is that essentially saying? Okay, if I told you that f of x was equal to a number, and I said that f of x plus 1 was another number. So if I say f of x gives me 1, f of x plus 1 gives me 2. Can you tell me how I got from the first one to the second one? Could you identify what the rule was? And what happens if I said another, say x plus 2 turned out to be 4? Do you know what the rule is? How do I go from 1 to 2 to 4? Do I just double? Could I count it using counting by threes? 1 to 3, and then what end up going at next would be 9. Multiply by 3. What I want you to take away from that is f of x is 1 point. F of x plus 1 is the next point, the next place that we are going to go. And by setting it up and looking at this, we are able to figure out what the growth is. How did I get from here to there? That's what that gives us. Kind of like pulling teeth. One of the things that we're going to talk about, and I'm sure you guys love physics, delta y over delta x. Change in y over the change in x. How is it changed? Well, that's just slope, right? And so you guys know how to go and figure out what the slope is between any 2 points. The average rate of change. Given a set of coordinates, you can go through and do that. So here the average rate of change was -3, -3, -3. Ratio of consecutive outputs, 2 to 5, 1 to -2, 4, 4 to 7. Make sure you always take a look at the patterns that are being identified here. Now here, that was -16, -8, -4, -2. Look at this, half, 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 half. One of the things that we need to do is determine whether a function is linear, exponential, or neither. Okay? For those that are linear, the linear functions, that models the data. So if I'm looking at this, is the average rate of change the same? Okay? Every time I do this, it's going down by 3. Linear function. When I take a look at this one's going down. It's not going down by a linear function. It's going down by a specific amount. What is that specific amount? Well, we take a look at the ratio, and we see that it's by half. Exponential. That's the difference there. And now this one here, 2, 3, 1, 4, 5, it's going up by a predictable amount. But the ratios, are the ratios the same? No. So that's neither. That's nothing. That's not linear. That is not exponential. It's something else. We just don't know what it is yet. So, graphing something like that. Like you said, pop it into the calculator, go from there. Not a big deal. You'll notice that this graph does have some qualities to it. -10. Remember, if I got a negative exponent, 1 over 8, because that would be 1 over 2 to the third power. What is 2 to the third power? 8 over 8. So when I got the negative exponent in there, I am going to end up seeing fractional or fractions, decimals, small values. Is this thing ever going to be able to touch the x-axis? In other words, is there a value that I can put in for the exponent that would make it equal 0? The answer is no. Not going to happen. X is going to end up having an S. It'll always have some kind of a horizontal asymptote. And this just goes off into infinity. So, if I look at this, number of cell phone subscribers at year end, does that look like exponential growth? Kind of. I can use exponential growth to identify what's going on here. Okay? So, properties of exponential functions. If a is bigger than 1, then what you are going to see, domain is always going to be negative infinity to positive infinity. Range is always going to be 0 to infinity. From 0 to infinity. Remember, it's not including it. No x-intercept, y-intercept is 1. The x-axis is always going to have that as a horizontal asymptote. As x goes towards infinity, okay, or towards negative infinity, the limit is 0. This is, well, we haven't really talked a lot about limits at this point in time, but a limit is where is it going to? Where does it tend to? Okay, won't hit it, but that's where it's going to. So on 4 there, an increasing function is going to be 1 to 1. That means I can come up with an inverse. I can graph the following points, 0, 1, 1a, and -1 over 1a. We'll always have those points. The graph of it's going to be smooth and continuous and no corners and gaps. Now this is if a is greater than 1. What happens if a is between 0 and 1? Now we do not talk about this thing being negative. We only talk about the values for x being, or the value of a, the growth factor, between 0 to 1 or bigger than 1. So you have a growth factor of 1, is it going to do anything? No, it just keeps multiplying by 1. The domain is going to be exactly the same from negative infinity to positive infinity. The range is going to be exactly the same from 0 to infinity. There will not be any x-intercepts, the y-intercept will again be 1. X-axis, A is a horizontal asymptote. Now we start seeing some changes. As x approaches infinity, it is going to go to 0. Think about this for a second. If I take a look at these two graphs, on the one on the left, a is 2. On the one on the right, a is half. If I go and put in negative exponents, that means things flip around. We end up doing a reciprocal thing to it, if you want to look at it that way. What's the reciprocal of 2? Well, that's half. What's the reciprocal of half? Well, that's 2. So this ends up being larger over here. As it keeps getting bigger, it keeps getting smaller and smaller and smaller. The left one we would classify as growth. Is it getting bigger as we go from left to right? What's the one on the right? One is growth, the other one should be what? Don't say that. Okay, so you got growth. These are the two things that we're looking at when we are dealing with this. Okay? So, we can graph these things using transformations exactly the same way that we've done in the past. Okay? We got a negative up here. That negative is going to force it to flip. Minus 3, that's going to force it to come down on the y-axis. Transformations are going to be exactly the same. Nothing new. Now, there is another number that you guys are going to have to deal with, and that's the number E. Grab your graphic calculator. You will see right down by natural log, right above here, ln, and then there's going to be a little e up there. If I go and hit second natural log, I get e, and I'm going to put in 1. This is the value of E. 2.718, it just keeps on going. It has the same set of properties as non-terminating, non-repeating decimal numbers. And the goofy thing is this actually shows up quite a bit when we're taking a look at different number systems, different ways of expressing things in an exponential number. Yeah. The other thing is, if I take a look at this, 1 plus 1 over n to the n, this actually approaches this. If we've taken a look at, we did a little bit of this last year when we took a look at compounding interest. You know, if we have it annual, we have it semi-annual, we have it every 6 months, we have it weekly, we have it daily. The more often we compounded something, the closer we actually got to this term of E. And when we actually did compounding continuously, E was part of that equation. So it really comes into play a lot often when we have something that happens over and over and over again in a really short period of time. The whole idea of continuous. Now, you can kind of see the progression here, how it goes. N 1 over n, what the number is, you get 1 plus 1 over n, and as we keep repeating that out for larger and larger values of n, we get closer and closer to this 2.7. I haven't given you many specifics yet, have I? because everything that we have here is simply building off of what we've got. Nothing new is being added here except that you're dealing with this in the total. Okay. Solving exponential equations. This might not necessarily seem as obvious as you'd like to think. So, I want to solve this. Could I go through and use the calculator to go through and do this? Most definitely. Now, when we're dealing with exponential equations, is it possible to write things in terms of prime numbers to some power? It's what you got to kind of think about. What is 81 in terms of prime numbers? Well, 81 would end up being 3 to the 4th power, right? Because 3 times 3 is 9, times 3 is 27, times 3 is 81. So if I've got 3x plus 1 is equal to that. If these bases are the same, can I just go and do a little substitution and say that this is going to be the case? Does that follow for you? Now, problem comes in over here. Do I have the same bases? And the answer is no. Can I rewrite this? Can I rewrite 4 in terms of a prime number to a power? So that would be 2 squared, right? And this would be 2x minus 1. What would 8 be? 2 to the 3rd power times x plus 3. So now I could rewrite this as 2. This gets distributed, so that would be 4x minus 2 is equal to 2 to the 3x plus 9. Can we go through and solve for x now? Yeah. We know that 4x minus 2 is going to be equal to 3x plus 9. We can just go through and do the solving. So that's one way of dealing with that. So, let's see. I don't necessarily think there's anything else I wanted to cover. There's your summary, and I'll let you guys get to work on this.